Hello, hi everyone. Welcome back to Radiant Semiconductor's technical presentation on the importance of timing constraints. So previous week we discussed about design margins, which are very important because design margins are the extra pessimism that are introduced in terms of design uncertainty, which covers the expected timing hit of every stage in implementation cycle so as to achieve targeted frequencies well in time. Right, it is very much required to have a right estimate of design margins. Right, this imparts the importance of timing constraints in VLSI. Now we also studied underestimated design margins, similarly overestimated design margins previous week. Right, so let's recap what are underestimated and overestimated design margins. Okay, so the scope of timing optimization reduces as we move down the implementation flow, right? So it becomes very important to judge the setup timing degradation hit in advance to achieve the targeted design frequency at the end, right? As we move down the ASIC flowchart all the way from RTL to synthesis to DFT to physical design to STA, right? It becomes very difficult to optimize the timing as we move down the implementation flow, right? The more we take control of timing optimization at the very beginning stages of the ASIC flow, the more it will be useful for us. Okay. Now, if design margins are not enough for any stage, it will not be possible to close design targeted frequencies. It will directly impact design performance. Okay, so this is the requirement of underestimated design margins. So we need to make sure that whatever the margins we are keeping, they should be sufficient and they should not be like not enough for any design stage. Okay. Similarly, when we go for overestimated design margins, for any stage, if design margins are chosen overly pessimistic, right, it will result in extra timing optimization, which might not be required, right? Obviously, so when we go for pessimistic timing margins, then it will lead to increase in area, it will lead to increase in power consumption, which may not actually be required. Okay, so overall, we are gaining in terms of timing by pessimistically optimizing the design, but on the other side, we are losing the design in terms of excess area consumption, in terms of excess power consumption. Okay, so this results in extra consumption of silicon area and power. The impact is SOC designs would not be cost effective. Also, bad power numbers may result in poor battery life, right? Because nowadays most of the equipments they are based on the battery. So when it comes to battery life, right, so the less power consumption, the more battery life, right? If the power consumption itself is more because of pessimistic design margins, right, then unnecessarily we have to add additional battery supply or we have to look for other source of power supply, right? So underestimated and overestimated design margins are two important things which we have to consider during design margins. It should neither be underestimated where we don't have enough design margins for a given stage, or it should neither be overestimated where we are choosing overly pessimistic margins. Okay, now general SOC flow and impact on design frequency, right? So this, let's recap what we studied previous week. So the below diagram shows general SOC flow all the way from synthesis and concludes at the noise closure, right? So synthesis followed by placement, followed by clock tree synthesis, followed by design routing, followed by noise closure, followed by timing sign off, right? So this is the general SOC closure flow what we have, right? So synthesis, we begin with synthesis where we map the RTL into technology dependent gate level netlist. Then we take that netlist forward for physical design, right? And then in physical design, we do placement where with ideal clocks, we are trying to optimize the timing, followed by clock tree synthesis where with propagated clocks, we optimize the timing, followed by routed design where actual net delays will be reflected, right? Actual R&C will be reflected, followed by noise closure where SI related things we are planning to close, right? So first step as per correct by construction is please focus on non-SI timing closure followed by SI closure, right? So that's where like design routing followed by noise closure. Noise closure again it includes glitch as well, right? I mean apart from the noise related violations what we have, timing related noise violations, we also need to take care of the glitch violations. And finally, timing sign off. So timing sign off is something which we have to focus on, right? So which is nothing but your STA, right? So the first step of physical design SOC closure flow is synthesis, right? During synthesis stage, the exact timing degradation due to placement, clock skew, interconnect delays and noise is not known, right? Because we are at the very beginning stage of the ASIC flow, right, where degradation due to placement, degradation due to clock skew, degradation due to interconnected delays, degradation due to signal integrity is not clear, right? Of course, nowadays we have physical aware synthesis, right, which to some extent will help us to understand how the timing will look like during the placement stage, right? Even we have option in the CCD where we can enable CCD very early in the synthesis stage itself, right? During that time as well, we have option to understand how useful skew can be considered, how we can do clock push and pull, right, in order to take advantage of the CCD, so that we don't have to completely depend on the data path optimization. We can also depend on the clock push and pull, right, for timing optimization, right? And then we have interconnect delays, right? Interconnect delays means during routing stage we'll come to know the exact R and C values. So these R and C values will help us to understand how interconnect delays will be present, right? And noise, signal integrity. Only when we have actual routing done, then we will have the noise, right? So during synthesis stage, timing uncertainty corresponding to above parameters has to be modeled properly for efficient timing closure, right? So that's the reason we have to model the parameters, right? For example, what is the clock skew, what is the clock latency, what is the interconnect delay, right? What is the uncertainty we need to keep in order to model the placement timing, where cells will be placed legally, unlike the synthesis where even the physical aware synthesis, even in physical aware synthesis we use course placement, right? Not the legalized placement. So a slight displacement is expected when it comes to the course placement. Okay. So effective frequency for timing path is maximum at synthesis stage. Now at placement stage, the designer is aware of timing degradation because of placement, but not due to clock skew, interconnect delays and noise. So at placement stage, timing uncertainty need not include placement margins. Based on the above reasoning, it is clear that the timing uncertainty should be different at different stages of the design. Timing margins for different stages. This is very, very important. Okay. Now let's look at different timing margins, right, which we have to include so that we can accommodate or we can model the design changes that are coming up during placement, CTS, routing, right? Those all changes can be modeled at the very beginning stage itself. That is nothing but synthesis stage. Okay. So timing margins, uncertainties for different design stages, PLL jitter. So PLL jitter value, which indicates the edge shift of PLL clock from one edge to another, is very crucial factor while timing setup path, right? It can either be considered in uncertainty or can be made part of clock period, right? Making it a part of clock period make more sense as it should be adjusted in case of multi-cycle paths, right? So this is PLL jitter, right? So PLL jitter value is something which we have to consider in the uncertainty, because PLL jitter value will impact your clock period, right? So that should be part of your uncertainty, which is nothing but your timing margin, right? Then there are two types of PLL jitters. One is cycle to cycle jitter, another one is long term jitter. So cycle to cycle jitter means jitter between two consecutive edges, right? Long term jitter, it provides maximum possible jitter to be considered for multiple cycle paths, right? To maintain pessimism in correct way, it is better to make it a part of clock period, and for multiple cycle path, it can always be checked whether n into cycle to cycle jitter or long term jitter should be considered, where n is multi-cycle value, right? So there are again different type of jitters actually, right, coming from the PLL. It can be cycle to cycle jitter, which is nothing but jitter between two consecutive edges, or it can be long term jitter, which is nothing but maximum possible jitter to be considered for multiple cycle paths. Okay. Or the third type of jitter is half cycle jitter. So half cycle jitter specifies the edge shift between rise and fall edges. all half cycle paths should be closed after factoring this half cycle jitter uncertainty. So these are the three different types of jitters, I would say, which needs to be considered in your uncertainty. Okay, so that the clock that is coming, right, the clock with this jitter, right, we are able to model the jitter and then take that into consideration while calculating the clock period. Okay, this has to be made as part of the clock period in order to make more sense, as it should be adjusted in case of multi-cycle paths. Okay, right. Then let's go to placement timing jump. Okay, as I mentioned in my previous explanation, so in synthesis we are going with non-legalized placement, right, which we call it as coarse placement. But then when you come to placement, it is nothing but your legalized placement, right? Now, during legalized placement, there is a chance of slight displacement which can occur, right? Because of this displacement, there is a possibility that whatever the timing we are seeing at the synthesis may degrade because of placement, right? Now, this is called as placement timing jump. Since physical location of design instances is not known during logic synthesis stage, the timing degradation is bound to happen while moving from synthesis to placement stage, right? Moreover, the synthesis tool generally has better logic optimization capability, so it is better to keep extra timing margin at synthesis stage, which is removed at placement stage to negate the timing degradation impact because of placement. This is very, very important. Placement timing jump, right? So we have to make sure that the placement timing jump is considered, right? Because in the placement stage, right, ideally when we go for legalized placement, right, as compared to the coarse placement, if we are doing physical aware synthesis, or as compared to the logic synthesis, right, then in that case the timing degradation is bound to happen. Okay, this also has to be considered as part of the uncertainty. Okay, so so that this timing degradation impact can also be counted when doing the synthesis optimization. Okay, next, clock skew, right? So clock skew determines the allowed skew while clock tree synthesis. Too low skew numbers can lead to increase in clock latency and can impact us with increased OCV effect and dynamic power. And at the same time, too relaxed skew targets can cause too many hold violations. This is also another problem. Okay, so skew numbers, right, it will lead to increase in clock latency, right, and can impact us with increased OCV effect and dynamic power consumption. As we know, as more the latency is, right, then automatically it will increase your OCV derating factor, which will increase your dynamic power, right? And at the same time, relaxed skew targets can cause too many hold violations. Okay, so the skew number should neither be low nor high. This is very, very important. Okay, so because in the end you need to make sure that your setup and hold both are balanced out, right? So that is where we need these numbers to be taken into account. Maximum range can be figured out by using following formula for a typical hold critical path, right? Skew max less than or equal to clock to queue delay of flop 1 plus net delay from queue of first flop to input, right, D or SDI of second flop, hold time of second flop. Above value should be justified with minimum latency of clock. Note, CTS tools generally work in single operating mode, but as the sign-off analysis is always done in OCV mode, clock skew should be measured after switching to OCV mode, right? In case of clocks with a different top level source latency, we also need to have interclock skew uncertainty. That is very, very important, right? Now, OCV margin, what are the different OCV margins which can be considered here? Various factors for on-chip variation are IR drop, layer to layer metallization mismatch, CMP induced metallization variations, transistor level VTH mismatch, transistor level mobility mismatch, intra-die temperature variation, toggling activity mismatch related to transistor aging, right? These are the main OCV related things which we have to consider. To cover the factors listed above, right, timing derivatives are applied for both setup and hold check, considering the average clock latency and taking care of CPPR, right, clock pessimism removal, right. OCV impact can be estimated. It should made part of uncertainty at pre-CTS stage to negate the setup timing impact visible after the application of actual OCV derates at post-CTS stage, right? So when we are finalizing the derates, it can be flat derates, it can be AOCV, it can be POCV, it can be LVF, right? There are so many different type of derates which are available, and whenever we are finalizing the derates, we need to make sure that the following above parameters, that is nothing but IR drop, layer to layer metallization mismatch, CMP induced metallization variations, transistor level VTH mismatch, transistor level mobility mismatch, intra-die temperature variation, toggling activity mismatch, right, which is related to the transistor aging. All these things are taken into account, right? It should made part of uncertainty at pre-CTS stage to negate the setup timing impact visible after the application of actual OCV derates at post-CTS stage, right? Now, noise margins, right? So noise margins, once a design is timing clean after routing stage, crosstalk analysis can induce some change in net and cell delays, right? A margin needs to be set for this as well during setup and hold optimization, right? This is very, very important. Noise margins are very, very important, which we have to consider, right? Now, apart from the design stages and uncertainties, above discussed factors define the required timing margins to be applied at the early design stages for successful timing closure, right? With every progressive design stage completion, timing margins reduce. Following is the way to model it with every design stage, right? So noise margin plus OCV margin plus clock skew plus place margin. These are very, very important, right? So this will dictate how the noise margins, OCV margins, clock skew, placement margins, these all things become part of the uncertainty, right? Now this is in synthesis stage, as you can see here. Okay, so in synthesis stage, the uncertainty is including noise margin, OCV margin, clock skew, place margin. Now, as you move to the physical design, right, in the placement stage, where you are legalized the cells and then we are analyzing the timing using the ideal clock, then the uncertainty value is determined by noise margin, OCV margin, clock skew. So no more we need the place margin because already we are in the placement stage, right? Now, once you go to the CTS, then uncertainty value is determined by noise margin and OCV margin. No more we will need clock skew. Lastly, when we go to the OCV stage, we just need the noise margin, right? And finally, right, when we are going to the SI and sign off stages, then we can make uncertainty equal to 0, right? So this is how we are taking care of the uncertainty values, right? But then when we make uncertainty equal to 0, we need to make sure that jitter is assumed to be modeled in the time period. This is very, very important, right? So jitter is no more modeled in the uncertainty. Okay, now let's go to the design margins for partitioned blocks. In designs where blocks are implemented separately, it is very important to consider extra interblock margin along with block uncertainty in block constraints because new timing violations can pop up due to the partitioning approach. There can be 4 types of timing paths across block. Okay, so interclock path, right? Interclock path where like you have clock 1 coming to flop A and clock 2 coming to flop B, right? And similarly clock 2 coming to flop C. Now interclock path means the flops which are getting different clocks, and intra-clock path means the flops which are getting the same clock. Okay, now intra-clock reg to reg path between B and C, right? And then input to reg path, interclock reg to reg path between A and B, register to output path, right? Please don't get confused between inter and intra. Intra means the same clock, inter means different clocks. Okay, now for path 1 we have already discussed how uncertainties will be modeled with respect to various design stages, right? So interclock uncertainty, to cover path type 2, 3, 4, we need extra uncertainty that will consider the uncertainty required for top level design closure. Top level uncertainty depends on the top level skew, OCV effect and the noise effect. Why? Top level allowed skew between different clocks, interclock skew. V, Noise effect margin on block from top. Yes, top level OCV impact on clocks. It can be judged by derating the expected uncommon clock path at top level, right? Consider the above factors. Top level uncertainty TU equal to Y plus V plus S, right? Where Y means top level allowed skew between different clocks, interclock skew, right? V means noise effect, right? Margin on block from top, right? And as I mentioned, inter means two different clocks, intra means same clock. S means top level OCV impact on clocks. It can be judged by derating the expected uncommon clock path at the top level, right? For path type 3, the updated uncertainty is interclock uncertainty is equal to U block plus TU. For path type 2 and 4, the updated uncertainty is interclock uncertainty equal to U block plus TU by 2. The above discussed top level additional uncertainty needs to be added while blocks level closure irrespective of the block level stage. Added complexities due to timing modes merging. Consider a partitioned block having two clocks, clock 1 and clock 2, and two timing modes, M1 and M2. Following are the valid worst case timing paths that cover the complete timing sign off within the partitioned block. Clock 1 to clock 1, 500 MHz, which is nothing but time period 2 nanosecond. Clock 2 to clock 2, 200 MHz, time period 5 nanosecond. Clock 1 to clock 2, 400 MHz, time period 2.5 nanosecond, right? Clock 2 to clock 1, 400 MHz, time period 2.5 nanosecond. To meet timing requirement for the above block, following approaches can be followed. The basic approach is to create two different timing modes and meet timing in both the modes. This approach is optimal for area and power but may not be optimal for design cycle time as it can lead to multiple iterations. The better approach will be to create a single mode having clock 1 frequency at 500 MHz, time period equal to 2 nanosecond, and clock 2 frequency at 250 MHz, time period equal to 4 nanosecond. In addition to this, a negative uncertainty which makes timing path optimistic of 0.5 nanosecond is applied between clock 1 and clock 2, and a negative uncertainty of 1.0 nanosecond is applied between clock 2 and clock 2. In this way, all the valid timing requirement of partitioned block can be met in a single mode without any extra pessimism, right? Now, to conclude, right, the above discussed design margins are technology dependent, right, and are different at various stages of the design, maximum at initial and minimum at final stages of the design. Please remember this, maximum at initial and minimum at final stages of the design. These margins, if applied optimally, will help in efficient timing closure of the design to achieve higher yield without having any negative impact on area, power, and overall design cycle time. Right. So this concludes the importance of timing margins, right? So in summary, please make sure that it is neither underestimated nor overestimated, right? It should be in a balanced way so that we can optimally use the timing margins, right? We can optimally use the timing constraints in VLSI for closure of timing without impacting the area and performance, okay? And similarly, power consumption. So with this, we'll wrap up today's timing importance session, and next week we'll catch up with another interesting topic in VLSI. Thank you all.